Okay, I'm back to using the Audible headset, the one that you can hear better, so hopefully this will work better. We're going to talk a little bit about acids and bases today, and I'm not going to go into a lot of detail yet. We're going to talk about acids and bases a lot more in the next unit. One thing that we will do a lab on in a couple of days is the titration. Um, and we're going to talk a little bit about a neutralization reaction, what that looks like today, and then we'll talk more about the titrations as we do the lab. I don't think anyone did a titration last year because nobody made it to acids and bases. So this will be new a little bit for you. The stuff that we're talking about today I think will be pretty straightforward. I think you guys will remember it. Okay, so for now, when we define an acid, we're going to say that it's anything, when you put it into an aqueous solution, it forms H plus ions. Okay, so in other words, for it to be an acid, for our definition for right now, it has to have hydrogen attached to it, which we've talked about that before. An example of that is something like HCl. When you put that in a solution, it breaks apart into H plus and Cl minus. Okay. Now the other thing we talked about the other day was weak versus strong electrolytes, and that really comes into play here with acids and bases. Okay. So actually, let me go back for a second. These things are also called, like hydrochloric acid is called a proton donor, because an H plus ion, if you think about it, hydrogen has one proton, one electron, and that's it. And so to be H plus, it has to give up its only electron. So then it is essentially just a proton. Okay, so an acid is called a proton donor because it's giving a proton into the solution, because an H plus ion is basically just a proton. All right. 7 strong acids, and these you have to know. Okay, you need to know these. They're going to come up time and time again throughout the year, so you just need to know these 7 strong acids, memorize them, make sure they are in your brain. Okay, and there's no good way really to remember this. If you want to come up with a mnemonic for it, I mean, they all start with H, obviously. So you've got chlorine, bromine, iodine, nitrate, sulfate, chlorate, and perchlorate. Okay, so those are the different anions that you have that make the strong acids. And this is just, it's extremely important that you know these. Okay, because everything else that's an acid that is not these 7 is going to be a weak acid. Okay, and you need to know the difference between strong and weak for a lot of different reasons in this class. All right, now bases. Any substance that accepts H plus ions, in other words, takes them or reacts with them, we're going to call that a base. Now, the kinds of bases we've talked about so far have been things like calcium hydroxide, CaOH2, or maybe lithium hydroxide, that sort of thing. Okay, what happens when you put those in a solution? They actually split apart into Li plus and OH minus. Okay, and OH minus hydroxide is a base. Okay, if something increases the hydroxide ion concentration, then it's a base, because OH minus will react with H plus to make water. Okay, put this together with this, and it makes water. So anything, for now, a pretty good definition for our strong bases is anything that dissociates to increase the concentration of OH minus in the solution. Okay. Now there are things that don't have to have OH minus attached to them in order to increase the OH minus concentration. That's where it gets a little more complicated, and that's where we start talking about the weak bases and stuff like that. But for now, the strong bases all have hydroxide on them. Okay. So the alkali metals are strong bases. Every single one of the alkali metals combined with hydroxide is going to be a strong base. So that's like lithium hydroxide, sodium hydroxide, potassium hydroxide. Any of the alkali metals combined with hydroxide, those are going to be strong bases. Okay, and then some of the alkaline earth metals are too: calcium, strontium, barium. Those are the ones that are a little bit further down on the periodic table. And the reason that the magnesium and the beryllium are not is because those aren't very soluble in water. So BeOH2 and MgOH2. If you look at your solubility rules, those are not very soluble in water, so they're not going to be strong bases because they just don't dissolve when you put them in the water. Okay? If they don't dissolve in the water, then they're not going to dissociate or separate into ions. Alright, so there's our strong bases. Alright, so we've got three acids here, okay, HX, HY, and HC. And the water molecules have been taken out, so this is just showing the actual acid molecules, okay? And we want to figure out from strongest to weakest, okay? Now, we talked the other day about strong electrolytes versus weak electrolytes, and the difference between them is the strong electrolytes completely dissociate in water. They completely split apart into their ions, okay? The weak acids dissociate a little bit, so they're weak electrolytes, okay? Some of it dissociates, some of it stays together. And then the non-electrolytes don't dissociate at all in water, okay? So we're looking at these three. The strongest acid is going to be the one that dissociates the most. And so you can see this HY right here. None of it stayed together. It all dissociated or split apart into positive and negative ions, okay? So this is going to be our strongest right here. And then to figure out our weakest, we need to figure out between HX and HC which one has more molecules that stayed together. Okay, so the HX we've got, and maybe we can count ions here too. So the HX, we have 1, 2, 3, 4 ions, 4 molecules that dissociated. I mean, really, it's 2 molecules that dissociated, right? And then in HC, we've got 1, 2, 3, 4, 5, 6 ions running around in that solution, okay? So the HX is actually going to be our weakest acid because it dissociated the least. It actually, most of the time, stayed together, okay? It did not split apart in the water. And then the HC is going to be the one that's sort of in between, or in the middle. Okay, hopefully that makes sense. The idea is just how much does it dissociate. Okay, classify each of the following dissolved substances as a strong electrolyte, weak electrolyte, or non-electrolyte. So we just talked about that. Let's go through each one of these one at a time. Alright, calcium chloride is not an acid or a base. It's just an ionic compound, okay? And remember, we got to look at our solubility rules here, okay? But you might know this one already. Most chlorides are soluble in water. Calcium chloride is definitely soluble in water. And actually, we just did this one for the lab the other day, right? You had calcium chloride solution in the back. You added it to the unknown carbonate, and the calcium carbonate precipitated, became a solid. But the calcium chloride is completely soluble in water. So, because of that, it means that the CaCl2 is going to completely split apart into Ca2 plus and Cl minus. And actually, it's really going to split apart into 2 Cl minuses and 1 Ca2 plus. So that is a strong electrolyte, okay? This one's going to be strong. The HNO3, well, this is an acid, right? So how do we know if an acid is a strong electrolyte or a weak electrolyte? Well, it depends on whether it's a strong acid or a weak acid, okay? Strong acids are strong electrolytes. What strong acid means is it means they completely split apart when you put them into water. And if you look back on your list, nitric acid is one of the strong acids. So this one's completely going to break apart into H plus and NO3 minus. None of it's going to stay together. So it's going to be like HY on the previous example. It's going to completely split apart into ions. Okay? So this one is also a strong electrolyte. And the reason we know that is because we have memorized our list of strong acids. Okay, C2H5OH, that's ethanol, okay? Well, that's not really an acid or a base or an ionic compound. This is just a molecule, right? So when that gets put into water, it's not going to dissociate at all. It's not going to break apart. That's just a molecule, so this is going to be a non-electrolyte. Ran out of room. Okay, but that's a non-electrolyte there because it's just a molecule. HCHO2 and they put in parentheses there, that's formic acid, okay? So formic acid is not on our list of strong acids. That means it is a weak acid. Anything that's not strong is weak, okay? So because this is a weak acid, it's going to be a weak electrolyte. That means it does not completely split apart in water. And then KOH, that's a strong base. It's also just an ionic compound that is going to split apart into K plus and OH minus. So that's going to be a strong electrolyte. Okay? Hopefully that makes sense, the difference between strong, weak, and non-electrolytes. Okay, neutralization reaction. When you have a strong acid reacting with a strong base, go back. Why did I do that? The net ionic equation is really easy to write. You're actually, and you might remember this from last year, the net ionic equation for a strong acid, strong base reaction is always going to be H plus OH minus gives you H2O. Okay? Now there is another way you can write the neutralization reaction that's also correct. Technically what's happening here is this isn't really H plus. When you put an acid into water, the H plus attaches itself to an H2O molecule and produces what's called H3O plus or hydronium. That's technically the more correct way to write an acid-base reaction. Okay, and so the other way that you could write this thing as a net ionic equation, there's two ways you could write it really, and one was on the other page. H plus OH minus gives you H2O, and they will accept that on the AP exam. Okay, or you could write H3O plus OH minus gives you 2H2O. Okay, and this bottom one is technically more correct, because really it's not H plus that's floating around in there, it's H3O plus. It's water with one additional hydrogen on it. Okay, so the protons, the H plus ions, they don't float around by themselves for very long before they attach themselves to something. And so really this is what's present in the solution, not the H plus. Okay, but again, either way is fine to write it on the AP chemistry exam. So going back to this for a second here, if you just split both of these apart, because this is a strong acid, hydrochloric, and sodium hydroxide is a strong base, so everything gets split apart into its ions, okay? And then you just look for the spectators. Chlorine and sodium are the two spectators here. When we cross those out, you get H plus OH minus gives you H2O. And that's going to be the net ionic again for every strong acid, strong base reaction. Okay, last sample problem here. Write a balanced, complete chemical equation for the reaction between aqueous solutions of acetic acid and barium hydroxide. Okay, so we've got HC2H3O2, and that's aqueous, plus barium hydroxide, BaOH2, also aqueous. Okay, now this one's kind of tricky because this is acetic acid is not on our list of strong acids. That's a weak acid. It means it's not going to completely break apart in water. But that doesn't really matter too much for this equation that we're writing right here. Okay, so for this equation that we're writing, sorry, hang on just one second. Okay, sorry about that. Okay, so what we've got here, again, is the acetic acid plus the barium hydroxide, and this is just a double replacement, just like we've been talking about. The hydrogen is going to come over here with the hydroxide, and the barium is going to go with the acetate, and we're going to end up with BaC2H3O2, 2, because acetate has a 1 minus charge, barium has a 2 plus. And the reason you know that is because you know your polyatomic ions. And that's going to be plus H2O, okay? And then we want to balance this thing, okay? We want a balanced, complete chemical reaction here. So we're going to have to put a 2 in front of this. And let's see what else we have to do here. So now we have 2 hydrogens, 4 hydrogens on this side. And we've got 2 hydrogens on that side, so put a 2 right there. And does that take care of our oxygens also? So then we've got 2 oxygens here. Okay, so that I think should be balanced at that point when we put the 2's in front there. Now, this is the tricky part. Okay, that's pretty normal. You're just doing a double replacement there. Barium acetate. Remember, acetates are always soluble. Okay, so that's going to be still aqueous. I didn't label it. This is going to be a liquid. All right. So here's what we have to decide, and this is tricky. The AP exam says you split things apart when they are excessively ionized in water. Okay? A weak acid is not excessively ionized in water. That means when you write the net ionic equation, you have to keep that together. Okay? So when we write this as a net ionic here, we're going to keep the acetate, or the acetic acid together here. So we've got H, C2H3O2. That's aqueous, plus the barium hydroxide. Now that is going to split apart into its ions. So that's Ba2 plus OH minus. And that gives us, we've got barium 2 plus on this side, because this is an ionic compound. Barium acetate is an ionic compound. Then we are going to split that apart. C2H3O2 minus, plus the water stays together because that's a liquid. Okay? So the only spectator that we can cross out here is the barium 2 plus. Everything else has to stay. So then we're going to write our net ionic this way. C2H3O2 aqueous plus the OH minus gives us C2H3O2 minus plus H2O. Okay, and then again, I think we have to do the same thing here where we put the 2 in front of this one and the 2 in front of the water, and then I think everything is balanced. No, take that back. You've got to put a 2 here also. And then are we balanced? Oh, and a 2 in front of the OH minus. No, that's not right. Let me go back here. Sorry. Okay, so when we have this thing balanced, we've got 2 of the acetates. We've got 2 of the hydroxides. We've got 2 of the acetates over here, and 2 of the water molecules. Okay, so everything should be balanced. Oops, wrong way. Everything should be balanced without any coefficients on this one. Just count and make sure. I don't think we need to balance this at all. We got 1 hydrogen, 2 hydrogens here, 1 oxygen. Yeah, everything's balanced. Okay, I was overthinking that one. So this is the correct equation here, the balanced net ionic equation, and that's what they're looking for on the AP exam. Okay, and this is really the tricky part on that one. Just recognizing when I write the net ionic, I don't split apart weak acids because they are weak electrolytes, and you only split apart strong electrolytes when you're writing the net ionic equations. We'll do more practice on that in class. Okay. That is it for today.